Hello. Greetings, my total physicist. Happy Friday. Hello, Teresa. Hello, Ellie. Okay, thanks for letting us know, Ellie. I hope your internet stays constant. I know how that is. Good. I got half my people. Let's see if I got Zach and Anne-Sophie on the way. I see 3, so let's see who else is here. Zach is here. Good morning or afternoon, Zach. Good. Okay, and I see 4, so perhaps I have Anne-Sophie here as well. I will put this aside. And yeah, okay, that's fine. In fact, I was going to start with that, Teresa. So let's see if you have any BAT questions to begin with. I know it was due yesterday, but if you want to resubmit it, you can if you still have a question. Let me go grab my copy of it, Teresa, which is right behind me, and then I can take your question on the last question. The last question is a very fun one, so I think you'll like it. Okay, hold on. Okay, let me read it, and then you'll understand what's going on. Explain why bats cry out in short bursts if they know the insect is closer, and longer bursts when the insect is far away. Okay, so I'm going to kind of do this. Ready? Pretend I'm a bat. There's my bug. Eh, 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 eh. Why do you suppose you want more short burst when you're getting closer to it? What does each burst tell the bat? Why do they need a lot more bursts when they're getting close to the bug? What do you think? Burst meaning every time they're sending an ultrasonic little tiny sound. Let me redo that. Ready? Here we go. And, and, and. Exactly. So Zach, you're on the right track. If I like that. If every time the bat makes a little sound, it gets a single tiny piece of information back as to where the bat is when it was receiving the echo coming back. But of course, when you're going to eat it, you really want to know where it is, don't you? So you need to not send longer burst, or I would say it's more time between the burst. And, and. But as Zach is hinting at, you need more information, more exact information. So for every millisecond where that bat is, so you can pop it right into your mouth and eat it. Okay? So more information, more bursts, more information. When it's far away, it's okay if I just go because I just want to know about where it is so I can fly that direction. But when I'm getting ready to eat it, man, I better have a lot of information so it can get it, because a bat's mouth is pretty small, right? Isn't that fun? I love that bat stuff. Any other bat questions on your mind today? Anybody? On Monday, I'll send you a sheet on earthquakes. That'll be our next wavy type equation. But we're going to continue on with light today. And what we're going to do is we're going to finish up the theories we began on light and then some other facts about light. Okay? Some of this will overlap with AP chemistry, Ellie, so it might seem a little familiar. Okay. Let's review last time. So people help me out. Type in. Light can be either a or a What are the two theories in a nutshell? Oh, yes, we'll do that in a sec, Teresa. What are the two theories in a nutshell? Light can be either a or a Yeah, particle or wave. Thank you, Zach. Exactly. Good. All right. Then we're going to connect those theories today in just a moment. Let's take Teresa's other question about the first two. Teresa, I think the main thing you need to know is what equation you're going to use. A says calculate the wavelengths of audible sound at 20 degrees C. So here we go. 20 degrees C, we're going to take the air. So we want wavelength, right? So we need what? V, use the wave equation. V equals the wavelength, lambda times the frequency. And for the frequencies, audible sound, ready? We're going to use 15 and 100. So we're going to do 15, use 15 hertz for one of them. And then it's 100 kilohertz. Well, that's going to be 100,000, isn't it? Because kilo's 1,000. So you got to use that twice, so to speak, Teresa. So that's going to be F, and that's going to be F. So use this formula twice. So I got the frequency, and I got the velocity, because the velocity, let's assume it's air. So the V is 344 meters per second. Why that one? Because they said it's at 20 degrees C. Okay. So use this formula twice, Teresa, and you can put in like 15 the first time and put in 344 meters per second, divide over to get your lambda. You're going to get two different wavelengths in meters. Okay. Teresa, is that enough to get you there? Oop, maybe I got a correction from Zach. I thought it was 1.5 kilohertz because it wasn't specified. Well, it says calculate the wavelengths, plural, of audible sound. Oh, audible sound. Ah, God darn it. Thank you, Zach. Ah, Anne-Sophie is here. Good. Thank you, Anne-Sophie. Okay, my apologies. Zach caught me here. I looked at the wrong numbers. So it's not 15, it's 16. So please change that, because it's the one that says, Teresa, people can hear waves from 16 to about 18,000. So it's not 100,000. That would be bats. Thank you, Zach. You caught me sleeping today on Friday. So the other one is 18,000 hertz. So Zach, what I think they wanted you to do is calculate both of those so you have a range. So you may want to go and redo that if that's what you didn't do, and just resubmit it. You know what I mean, Zach? And then that'd be fine, because you can still do that. I don't care if it's late. It doesn't matter. I haven't graded them yet anyway. All right. So, but they want two different answers, the wavelengths. So one for 16 hertz and one for 18,000 hertz, the two they give you for human audible hearing. Oh, okay. All right. Thank you. Okay, good, Zach. All right. Let's go to B. Teresa asked about B as well. Calculate calculate the wavelengths of echolocation frequencies used by the bat. Okay, it's the same thing, but it's the same equation. V equals wavelength times the frequency. And we're going to put in the bat numbers, Teresa. So this time your F will be, it's the ones I used wrongly for question A. 15 hertz. And then again, we're going to use this equation twice. 15 hertz and 100 kilohertz. So that'd be 100,000 hertz. And same thing is up here. You're going to use for the V 344 meters per second, 20 degrees. And I think that's it. So my question to Teresa, will that get you there? If you got your equation, and we'll talk about what to substitute in there. So is that okay? And then anybody else, any other bat questions? Good. Okay. Good, Teresa. All right, then. Without further ado, let's go ahead and talk about the theories of light. Now, Anne-Sophie, just before you got here, we said light can be either a wave or a particle. This was the two theories, and frankly, this was guys we haven't talked about yet. A Dutch guy named Huygens was really into the wave theory. Several people were into the particle theory. Why? Because they had experiments to back them up. Finally, we had an experiment that somebody did, and I'm going to now open up my notes, that really caused problems. So it's kind of cool to know what this is. It's called the Compton effect by Arthur Compton. And I think he won a Nobel Prize for this in 19 something or other. Okay, so Compton effect. Let me tell you where we're going. There's two theories of light. I want us to understand what they think about light today and why. So this was the last great experiment that helped figure out, okay, I'll make a bad pun, that shed a little light on light, okay? The Compton effect was this. It was a stream of electrons. Ready? Here they go. E minus electrons. They were shot this way. And what they did is they took some X-rays and they shot them at an angle. X-rays. And the X-rays went like this. And then they bounced off these. So they reflected. And you might say, so what? We know light reflects. Big deal. Here's the big deal. Once it reflected, the X-rays changed their color. Now you might say, well, they don't really have a color. Okay, they changed their wavelength. Think of that with water waves. Can you imagine water waves? Maybe that's the side of the pond. The water waves come up and hit this, and suddenly on the way back, they have a different wavelength. It wouldn't make any sense because waves don't do that. So let's see what they figured out. Like, what's an explanation for this? So why did the X-rays change their wavelength while reflecting? Why did they change their wavelength while reflecting? Okay, how many of you played table hockey? I hope all of you. Where they have little air vents and then the little puck goes and it goes really, it slides easily over the puck. The puck is what it's called. Slides easily over the table. Well, what I can do is I can take a hockey puck like this puck. And I can take another one like this. Here, let's take another color. Puck 1. Let's take puck 2. Okay, here comes puck 2. It's going to hit this one. And when it hits it, this one moves a little bit forward, doesn't it? Yeah, I'm going to write that in words. And then this one's going to go, and it's going to bounce off, but it's going to bounce off and it's going to change. It won't be going as fast. So it bounces off. So let me write that. Okay, so puck 2 hits puck 1 and bounces off or reflects off, if you like. Oh, my cat is whining outside the door. Jago, shh, shh. Sorry. It bounces off. Kind of a rude cat, you know. He interrupt us. Obviously, he doesn't give a puck about physics. Okay, so puck 2 hits puck 1 and bounces off, but with less energy. In other words, it's going to bounce off this other puck, but that's going to cause puck 1 to move a little bit. And I'll put a little arrow on puck 1. And then puck 2 bounces away. I'll say here less energy. When waves bounce away with, exactly, so air hockey, exactly right. So when waves bounce away and they have less energy, they have a different frequency. I think we said this with waves. The greater the frequency, the greater the energy. So if they have less energy with waves, less energy equals lower frequency and therefore also a different wavelength and a higher wavelength. If light was only a wave, it wouldn't do this. If light was a wave, it should just go boop, boop, and come back with the same energy, the same wavelength as when it bounced off, before it bounced off the surface. But this giving of energy means, here's the resolution, the solution, the conclusion. Thank you, the conclusion. Light is acting like a particle here. Light gives energy like a particle. So the people that were in the wave theory camp were not happy. Well, finally, there was a guy who figured out a and figured out an explanation for both of these theories. And by the way, we said earlier, I think, that because we get an interference pattern with light, it's like a wave, right? So that was good evidence for the wave theory. The Compton effect was good evidence that light is a particle. So particle wave, that's where we're at, okay? All right. A fellow from Berlin figured this out and explained the Compton effect, and became pretty famous. Said light is like both a wave and a particle. He sort of said our understanding of light is imperfect because light is light, but it doesn't neatly fit into our category of wave or particle. And the guy who said this was, of course, Albert Einstein. And we're talking like 1910, something like that. So over 100 years ago. And so he came up with a theory. You ready? It's not his Einstein theory of relativity. Instead, this theory, well, it's not really a theory. Let's call it an equation. Sorry. And it's this. E equals h times the frequency. Now, we might have had this in AP chemistry already, so Ellie and Anne-Sophie. If we did, bear with me, okay? Okay, so for Teresa and Zach, E here stands for energy of the photon. So what theory is that representing, everybody? If it's energy of the photon, this side of the equation with the big E must be what theory? What theory is this side? Energy of the photon. We got a lag, so I know I won't get your answers for a few more seconds. So punch in. What theory is that? Energy of the photon. When did we talk about photons last time? Yeah, thank you, Zach. Good. The particle theory. So this is particle theory. And the H we'll talk about in a sec. The F over here is for frequency. But that's what we use for waves. So that's the wave theory. So coolly enough, Einstein figured out an equation that related the particle and the wave theory together. I know there's a lag. I don't always get your responses very quick, so thanks. The H is Planck's constant. Named for another famous physicist by the name of Max Planck. You might have heard of the Max Planck Institutes. There's one for physics, there's one for chem, one for bio. There's several around. Mainly it's around Berlin, but they're elsewhere as well. So, hey, isn't it cool? A famous equation with two local fellows, right? Planck and Einstein. So this was named in Max Planck's honor, this constant. far out. So this is a way to go from one theory to the other, back and forth as you need be. This side is in joules, not surprisingly, in joules, right? Energy's in joules. And the other side is in hertz, right? Because that's what frequency is in. For the Planck's constant, you don't have to worry about the number. We're not going to do calculations with it in this class. I just want you to know it's out there. It's just a constant like pi. It's just a constant number. Yeah? So that, I hope, is kind of fun for you. I love the fact that we're in such an internationally and physics-wise, such an important place. Okay. I think I want to take a little time and talk about types of light. Let's see if there's any questions. I know there's a lag today, so I'll assume we're okay. That's the way it still is today, by the way. We still think light is like a wave and a particle. We agree with Einstein in this respect. Okay. Light is a cool thing. So let's talk about the wave type and applications. Remember, I have two goals for you in this course. One is to learn the principles and concepts and problem solving, all that of physics. But the other is to know where it's used in nature and technology, okay? Because I think that's the cool thing. What are the concepts, but where they're used in our world? So let's talk about, first off, radio waves. And we're talking like kilometers to tens of kilometers big. For the wavelength. And of course, radio waves are used for radio, right? So application, FM, AM, TV, communications, communication. Then we got microwaves. And this is on the order of like centimeters. So the wavelength would be in centimeters. And of course, the main use we know, it's also in communications, by the way, but it's used in, of course, microwave ovens. And here's the cool thing. Let's see. Yeah, thanks, Anne-Sophie. That is indeed Planck's constant, the number. You got it. I'll ask everybody, because I assume we talked about it in AP. What do the microwaves do to heat your food? So what do these little centimeter long waves do to heat your food in the microwave oven? Microwaves are a big enough wave to do something special with your microwave oven. They bounce around, yes, but they're going to hit something and they're going to do something exact to something specific in your food. So they do bounce around in there. And by the way, your microwave rotates because they're coming out of just one side. So they rotate around to warm the whole food. Actually, no, they're not coming out. They're coming out of two sides. Because you actually get an interference pattern. Here's a fun thing you can do if you're bored. All right, you got an extra chocolate bar around. Take everything out of your microwave. Take out the glass plate. Take out the circulating plastic ring, and put a piece of chocolate in there. You're gonna make a mess, so you're gonna have to clean it up. Turn your microwave on, and then stop and look, and you're gonna see on the chocolate heated up, not heated up, heated up, not heated up. And guess what you're going to have? An interference pattern from the waves coming from the two sides. You're going to have nodes and antinodes. Where it's heated up, those are the antinodes. Where it's not heated up, those are the nodes. How about that? proof that microwaves are waves. Okay. It does. It makes a certain thing vibrate. What they do, Zach, and everybody, is they spin or make oscillate. Actually, they spin water molecules, these waves. So they spin H2Os. And so if your food's really dry, it doesn't heat very well. So my hint is add a few drops of water if your food's a little dry, and it will heat better. So it spins. This sort of wave has that function, that it's the right size to spin the whole molecule. Huge. Okay. Yeah, it makes so to speak, it makes the water vibrate. Okay, let's go back to another one. Let's go to infrared. Infrared waves. And I don't even want to give you, yeah, I don't want to give you the amount for we can look up the amount, but we don't need to. It's more or less, application is it's a type of heat. So heat is an infrared radiation, okay? It's in that part of the wavelength. And it's a heat from, similar to something, Zach, you just said, from molecular vibrations. So up here, think of the H2Os doing this, okay? For the vibrations, they're not doing this, they're doing this. Here's a water molecule. They're going back and forth. Burp, 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 burp. Burp, burp, okay? So they're vibrating more. Here they're spinning with the microwaves. Okay? I say heat, and I mean from hot objects. Where I'm from in Montana, in the fall, a lot of hunters use infrared goggles, and they can look out and see if there's an elk or deer out there. And if they can see them and shoot them. Okay, so that's what's up in Montana. So heat from microwave ovens, and I'll just write here infrared goggles, or an infrared scope on the rifle as well, like a telescope, scope on the rifle. And that can also see the heat given off by a deer or elk from any warm object. It'll give off these rays. It's actually a type of light, even though we don't think of it that way. Yep, vibrations. If I don't want the cheese or chocolate to sizzle much, I add a small glass of water. That's a good idea. And then the water absorbs the energy, right, Anne-Sophie? Yeah, very good. Clever, practical science. Okay, let's go to what you and I know now. Ready? Here we go, visible light. And of course, visible light is, of course, what we can see. It's a tiny fraction of all light. So we don't see much, to be really honest. Let's go on. We'll spend a whole chapter on visible light, really, to be honest. Okay, the next is ultraviolet. And ultraviolet is really small, wavelength, really small lambda. Insects can see this. We cannot. And I'll come back to that in a second. What we get from this is can cause, as you know, sunburn. So it's something we often want to block. X-rays, obviously for medical use. And as a chemical tool. I'll write here X-ray diffraction. I have a unit called Tools of Light, and it's different types of light used to investigate molecules. We study one of these in chemistry. That's the spectrophotometer. Okay, or spectrometer. Okay, when we send ultraviolet light at atoms and knock off electrons. We did that in AP Chem. For this X-ray diffraction, it's a bit like investigating the distances between atoms. So X-ray diffraction, okay, examines molecules, to be really blunt about it. X-ray diffraction is how they figured out DNA and that it's a double helix. So it's a really valuable tool. And finally, gamma. I know I've about run out of room here. Is a type of radiation. Probably don't want to get a lot of that because it can harm your body. And it's very penetrated because they're such small waves. It can really penetrate the body. Not just the skin, but the flesh, the bone, everything. That I did not know. So dermatologists use UV light to treat warts. Well, that's cool. I told you about my buddy who treated warts, right? He worked in a lab where they had liquid nitrogen, and he kept dripping it on the warts, and pretty soon all his hands had little black spots all over it. But he was proud that he got rid of his own warts, even though his hands looked pretty awful for weeks. But it was free, and it was fun, apparently dropping liquid nitrogen on your skin, although it does burn your skin and turn it black. Anyway, don't try that at home, okay? Leave the liquid nitrogen to the experts. Ute, okay, let's erase a bit of that. And let's go to some things that we never think about, but we use all the time. I want to talk about the word transparent. You and I think it means like see-through, right? What it actually means that light goes straight through these items. And we're talking like glass, water, vacuum. To us, these are transparent. Glass, water, a vacuum. A vacuum is not a vacuum cleaner. A vacuum is an absence of molecules, like in space. Maybe you know that already. Absence of molecules. Think like outer space. There's a big vacuum out there. However, this varies with wavelength. Here's what I mean, okay? Here's a window. And here's like the house, okay? Here's you got a plant back here. It's like what you had in your book, I think, too. Here's a plant. Okay. Well, it turns out if I've got ultraviolet light does not go through. And it turns so it's not a glass here. This is glass. Glass in my window. Glass is not transparent to ultraviolet light. Ultraviolet light goes bang, bang, bounces off. Well, infrared light, which is called IR, it also bounces off. So it's not so the only light that gets through is visible. So if you want to get a suntan, and I'm not asking you to do this, but you would not want to be behind glass. Glass blocks UV and infrared light. So UV and IR, infrared light. Only visible light comes through, okay? What does it say under X-ray diffraction? It says examines molecules. And then under that, radiation. So X-ray diffraction, Anne-Sophie, examines molecules. Didn't Marie Curie die from too much exposure to gamma rays? It could be. I'm guessing she got cancer. And I don't know if it was the gamma rays that did her in and gave her cancer or other stuff. She dealt with a lot of radioactive material. So I don't know what sources contributed to her cancer. Could well be. Nice. Okay. Light travels by interacting with electrons in the molecules that light hits. Which is kind of cool if you think about it, because if I got a vacuum, so if I got a vacuum, outer space, light doesn't hit any molecules. So C stays C, keeps the same speed, right? No molecules, no electrons to slow it down. However, if I got light here, that would be in a vacuum. If I got light in glass, the speed, and if we can do it, we'll do a lab on this. If I ever see you guys again, I hope in March. And in glass, it's about 0.67 because it slows down. Why? Because it interacts with the electrons in the glass, and that slows the light down. So interacts with the electrons in the glass. Same with water. Water slows down light a bit too. It interacts with the electrons in the water molecules. Good. We're going to continue there next time. We're going to talk a bit about shadows, and maybe I'll do that at school. And Polaroid filters. You know what? I need to do that at school. So I'm going to do either a live stream at school with you next week, or I will record it and just have you, instead of a live stream, I'll have you just as an assignment, watch the video that I make. Okay? What else happens if light hits the International Space Station? Well, it'll bounce off. So then it'll bounce off or interact if it hits the solar panels and then generate heat on the space station. A lot of that space station is solar panels. Okie dokie. I wish you all a good weekend. So stay tuned next week for more on wave demos that I'll do at school and on your earthquake worksheet, which I'll send to you on Monday. Okay, be good until then and stay healthy.